Robotic arms and vision systems are used in many modern production lines. In this video, I will show you how to make your own pick-and-place robot, which can identify parts automatically and place them in the right location. Since I am not a robotics specialist, I learned a lot of new things while working on this project. I hope there is some useful information for you in here as well. I will show you how I use the Pixy2 module for pick-and-place tasks on simple cylinder-shaped parts using the Dobot Magician Robotic arm. An Arduino Mega is used to tie everything together and to make the arm perform tasks based on the input from the Pixy2 camera. I will go through the entire project in different sections, starting with how to connect the Pixy2 and the Dobot to the Arduino, the camera position and the mounting bracket, the camera settings and lighting, the calibration routine, the Arduino programming, followed by a pick-and-place demo with a gripper and a pick-and-place demo with a vacuum cup. Recently, I found an article on the Pixy2 Vision module, the 2018 upgrade to the original Pixy camera launched on Kickstarter in 2013. The Pixy2 is a nifty camera module with built-in part detection, which can track objects at 60 frames per second. It does not have the resolution, feature recognition, or any of the other fancy features of professional vision systems, but with the features that it does have, it's perfectly capable of handling less demanding object detection tasks. The object detection on the Pixy2 is based on blob detection, where something is recognized as an object when enough pixels of a similar predefined color are found in the image. Objects need to have a more or less uniform color across the part, which differs significantly from its surroundings. The Pixy2 does not recognize the shape of an object, so part identification based on geometry or finding the angle at which a part is rotated is not possible. Okay, so let's start with how to connect the Pixy2 and the Dobot to the Arduino. In this project, the Pixy2 and the Dobot Magician are connected to an Arduino Mega, which contains a program for controlling the pick-and-place routines. The Pixy2 is connected to the I2C bus on the center of the Arduino board. The Pixy can be connected using the supplied flat cable. However, since it's too short for this application, I made a new cable at the desired length. Flat cable connectors and the cable itself were purchased from a local electronics store. Since I do not have a crimping tool, I used a pair of pipe wrench pliers to crimp the connector, which is not advisable, but it works. Just a quick check with the multimeter to see if all connections are made properly, and we're ready for the next step. An LCD shield is placed onto the Arduino board with some female socket headers in between to clear the serial connector below the board. The ground pin on the Dobot is connected to one of the ground pins on the Arduino. The RX and TX pins from the Dobot are connected to the TX and RX pins on the Arduino. In this case, pins 18 and 19 are used. I've considered two options for where to position the camera, either in a stationary setup where the camera is mounted on a separate stand, or with the camera fixed near the end effector on the arm itself. Both options have their pros and cons. The benefits of a stationary setup is that the camera can register parts at the same time the robot is performing pick-and-place operations. This option leads to the quickest cycle times and may therefore be the best option for industrial use in a fixed production line setup. The drawback, however, is that the camera is separated from the robot arm and therefore needs to be recalibrated if either of the two are moved to a different position. This is the reason why I chose to mount the camera directly onto the robot arm. The position of the camera now only needs to be calibrated once and is still valid when the arm is picked up and moved to a different location. I've designed a camera mounting fixture which is used to fix the Pixy to the front of the robot arm. The part was designed in Fusion 360. There are a couple of requirements that lead to the current design. The camera should be close to the end effector, while making sure that it's at a position where the gripper or the suction cup do not block the view of the camera. In order to align the field of view of the camera as well as possible with the movement range of the arm, I decided to place the camera on the side of the end effector instead of mounting it directly in front. The camera is also slightly rotated, since the arm is also rotated at a certain angle when the camera is directly above the area where the parts are located. This angle does not have to be exact. It's only intended to get as much as possible of the picking area into the image, which would not be possible if the image was tilted. Any residual angle of the image will be taken care of automatically in the calibration routine procedure. A picture of the Pixy2 module was imported into the Fusion 360 module for visualization purposes and, more importantly, to transfer the location of the mounting holes to the fixture. Since the module is very light, it's sufficient to use only 2 of the available mounting holes. Standard M3 screws are used to fix the module and are screwed directly into the non-threaded undersized holes. With the camera in place, it's time to have a look at the calibration routine. The calibration routine basically makes it possible to transform XY locations in the coordinate system of the Pixy camera to the coordinate system of the Dobot. So each time a part is found by the camera, its location is transformed to the coordinate system of the robot arm, so it's able to pick up the part. Several factors need to be taken into account when trying to transform the coordinates. The routine I'm about to describe takes care of scaling in X and Y direction, rotation and translation. To keep things simple, I did not take into account skewed coordinates or lens distortions. I used some basic trigonometry to perform the transformations. First, the camera is moved to a position at a height where the entire work area is in view. A routine is performed where the camera searches for 3 calibration dots, one representing the origin of the coordinate system and the other 2 points at a random location at the X and Y axis. The distance between the points is not relevant, only that they describe 2 intersecting lines which are perpendicular to each other. The location of the calibration dots are stored in the EEPROM of the Arduino controller so they can be used later, even after turning the system off. Let's call the coordinate system of the Pixy System 1. The second part of the calibration routine is to move the robot arm physically to each of the calibration points as accurately as possible. These locations are also recorded in the EEPROM. We will call this coordinate system System 2. We now have all the data we need to transform coordinates from the first coordinate system to a corresponding location in the second coordinate system. This is performed as follows. First, the angle of each system is calculated as well as the scale of the X and Y axes and the distance between the origins of both systems. The coordinate is moved in X and Y by the same distance as the origin location of System 1. Coordinate system 1 is then rotated to make X horizontal and Y vertical. The X and Y axes are scaled to match the X and Y axes of system 2. Another rotation is made matching the angle of system 2. The coordinate system is then translated in X and Y by the same distance as the origin location of system 2. When all of this is done, we should have found the location of the part in the coordinate system of the Dobot, which is required to send the robot arm to the right location. Now let's have a look at the Arduino programming. For the Pixy2, a library has been made available for the Arduino, allowing it to be integrated easily into Arduino projects. The library for the Pixy can be downloaded from the Pixy website. I'll put a link in the description below. And it can be installed in the Arduino IDE by selecting the Sketch menu, then include library and add .zip library. Doing this also makes Pixy demo sketches available under the File menu. For the Dobot, no library needs to be installed. The Arduino program for this project consists of 3 main sections, which are also covered under 3 menu items on the Arduino LCD shield. I will go quickly through each menu item. If you would like to have more details on the underlying Arduino code, you can download the program from my website, uptimefab.com, link in the description below. I left a lot of comments in the Arduino program, but if you still have some questions, please leave them in the comment section. The 3 menu items are a jog menu for manually operating the robot arm, a run menu in which the automatic cycle can be activated, and a settings menu for calibrating the camera, setting positions for drop locations, etc. I have to admit, the menu system is a bit primitive, but I focused more on getting the system to work than improving the user interface. Let's go through the menu. After starting the system, a welcome screen appears. During startup, also all previously stored data is read from the EEPROM. After pressing any key, you end up in the first menu item, which is the jog menu. This allows the user to set the jog increment from 0.1 mm to 20 mm. The robot arm is moved with the selected increment anytime the up or down key are pressed. The current axis is displayed on the bottom right, including its position. Pressing the right arrow button changes the axis. All 4 axes can be controlled, X, Y and Z for the movement of the arm, and R for the rotation of the gripper. The vac option allows the user to manually open or close the gripper or activate the vacuum for the suction cup, depending on which one is selected. Menu 2 is for starting the automatic cycle, which will be demonstrated later in the video. In menu 3, the user can set the following parameters. Set the calibration position or move to the currently stored calibration position. Set or go to the Z down position, which is the Z position at which the parts are picked from the table. Set or go to the positions of calibration dots A, B and C. This is used in the calibration procedure. Set or go to the start position, which is the initial pose of the arm after startup. Set or go to any of the drop-off locations. Start the calibration routine and select if the enter factor is a gripper or a vacuum cup. For the gripper, both vacuum and compressed air are used to operate it, and for the vacuum cup, only vacuum is required. Now let's have a quick look at the camera settings and lighting. The way parts are lit has a huge effect on how well the camera is able to find parts. The parts may become overexposed when using too much light, or the opposite, the camera may not be able to recognize a color when the lighting conditions are too dim. I have found that there's not a lot of leeway for the lighting setup, and I have to regularly change the camera settings if the amount of ambient light is changing, for example at a different time of day. In order to get a correct exposure and visibility of the parts, you can play around with the background color of the table, the type of light source, the position and angle of the light source, and probably a lot of other factors. The Pixie itself also has a built-in LED to illuminate the scene, which could be another option. I've gotten the best results during daytime when just using incoming sunlight as a light source, but your mileage may vary. I will put a link in the description below to a very helpful article on lighting for machine vision systems. There are a couple of settings in the Pixie monitor software that can also greatly help to improve part detection. One is camera brightness. This sets the overall brightness level and can help better identify different colored parts. For each signature, there is also a setting called signature range. Set this for each color signature individually to prevent false positives while still picking up as much surface area of the part as possible. Go to Settings Camera. On this tab, you can choose whether the camera applies auto exposure and auto white balance. On the same tab, there's a setting called flicker avoidance. Enable this when using indoor lighting. This should eliminate the flickering effect. However, this makes the picture much brighter and can cause overexposure. To counteract this, turn down the light source until a good exposure is achieved. Now that we have everything set up, let's look at a pick and place demo with the gripper, followed by a demo with the vacuum cup. You may notice that the arm sometimes pauses between moves. I've implemented delays in the automatic cycle since I was not able to read back the current position from the Dobot. Therefore, I'm just waiting until a certain amount of time has passed to make sure the Dobot has finished the previous move. This is a pretty ugly solution, of course. There is a getPause function available from Dobot for reading back the position, but I wasn't able to make it work with the Arduino. So if anyone knows how to do this, please let me know in the comments. Thanks.